Kia ora koutou. Here are the achieved questions from the 2020 integration paper. So there are 6 of them and I'm going to go fairly quickly through all of them. So if you're in 13 MCA and you've got questions on these, send me an email and I can show you where to get some more practice questions that are similar. All right, so the first one, we have to anti-differentiate this function here. And the only thing we've got to watch out for in here is this 3 over x, which will anti-differentiate back to a log. So this will be 1/2 of x squared plus 2x plus 3 times the natural log of x plus c. Right, remember that the natural log of x differentiates to give me 1 over x. Okay, and you've got that on your formula sheet, but that should be really familiar by now. In the next question, we've got a kinematics problem, just like we used to have in level 2, only the function's got a fractional power in it. We've got velocity. Velocity is equal to 0.6 t to the 1/2, and we're being asked to find displacement of the object after 16 seconds, and we're told that when t is 0, v is 5. So we'll start by anti-differentiating 0.6 t to the 1/2. That gives us 0.6 times, leave a gap for the coefficient. Well, the power is going to go up by 1 to 3 over 2. When we differentiate it back, we're going to get this coming down. So we have to undo it by timesing by 2 over 3. Now we've got our plus c. So that gives me 0.4 t to the 3 over 2 plus c. Sorry, that's not v, that's s. And we know that the initial displacement is 5 when t equals 0. So 5 is equal to 0 plus c. That gives us c equals 5. So s of t will be 0.4 t to the 3 over 2 plus 5, giving us s at 16 seconds of 0.4 times 16 to the 3 over 2 plus 5, which is 0.4 times 4 to the power of 3. So I know you'll do this on your calculator, some of you, but the square root of 16 is 4, so then we need 4 cubed. So it's this. So 12.8 times 2, what have we got? 25.6 plus 5, so 30.6 centimetres for this one. Right, question 2. Well, you can see that we've got a Simpson's rule coming up in the second part of this. But the first part is just another straightforward anti-differentiation. I'm going to write it before I muck it up though as a negative power, so it's pi minus 2x to the negative 2 dx. I really recommend that you do that as well. That gives me pi x, and then I'm going to have x to the negative 1. When I differentiate that, I'll get a plus sign here. So, I'll get a minus sign coming from this, which means that I just want to have a plus here, and I need to have a 2 as well. Right, so just check back that when I differentiate this, I'm going to end up with the correct coefficient, and I have to have a plus c on the end. Right, in the next one, we've got values in the table to find an approximation to this integral using Simpson's rule. So when we use Simpson's rule, we're using the y values, and we're looking at the width of each interval, and that width is what we're going to call h. So in here, h is equal to 1/2. The formula for Simpson's rule is as follows. So a is equal to that width divided by 3 times the end points, and then 4 times the odd numbered points, right? So y1, y3, and so on, up to the one just before the end, and then 2 times the other ones. So it looks a bit funny, but it's actually pretty easy to use when you're given this in this context, because you know if you're given it, you're going to have the right number of things to make that formula work. So in here, what we're going to be doing is this in there once, and this in there once. This one, and this one will be 4 times. And then these ones will be 2 times. So working that out over here, we get 0.5 over 3 times my endpoints 1.1 plus 1.3 plus 4 times those three values that are the odd numbered ones, plus 2 times 2.1 plus 2.7. And when I add all of that up, we get 0.5 times 3 times 4.4 plus this is 6. 6 fours are 24. This is 4.8 times 2, so this is 9.6. Fine to do that on a calculator, but I think it's worth checking that you haven't screwed up a calculation in there, because in here this came out to a very nice 0.5 times 3 over 3 times 36, so 18 over 3, which is simply 6. Okay, hopefully you can see why that's only an achieved question. Once you've done a couple of them, it's really easy to work with both that formula and the even more straightforward trapezium rule formula. In the next question, we've got a trig derivative, a trig integral, sec 2x tan 2x. And hopefully by now you know that when we've got y equals sec of x, that differentiates to give us sec x tan x. So that's what we're going to be using here. This has come from sec of 2x. But when I differentiate that, because of the chain rule, I'm going to get a 2 coming out, which I have to undo. So it's going to be a half of sec x, sec of 2x, plus c. The last question is not too hard, but there is a little bit more work than you're used to seeing for a simple achieved question. And you should also see that we've got, we're going to be working with exact values. So dy by dx is equal to cos of 2x. That means that y must have been sine of 2x times 1/2, right? Because by the chain rule, when I differentiate this, I'm going to get a 2 coming out, and I need to undo it, plus c. We know that y was equal to 1 when x was pi on 12. 2 pi on 12 is pi on 6. And sine of pi on 6 is 1/2. So we've got 1 is equal to a half of a half plus c. So c is equal to 3/4. That means that we can figure out y when x is pi on 4 as follows. So it'll be a half of sine of 2 times pi on 4 plus 3/4. Sine of 2 times pi on 4 is just sine of pi on 2, which is 1. So it's a half of 1 plus 3/4, which gives us 5/4 or 1.25. So there you go, just 6 little achieved questions. I've just about finished this paper. I'll do the last of the merit ones later on today. Thanks for watching.